All right, we're going to look at a couple little examples here to learn how to calculate or figure out the direction of the magnetic force. So magnetic forces are going to be at play when you have charge that's moving through a magnetic field. And so what we're going to do is look at a couple examples of this. So if you look at this example on the left, we've got a magnet that's kind of glued in place, so we're going to not allow this thing to move. And then up above it, there's going to be a circuit that happens to be running. So somebody has rigged this up, so we're operating a circuit up here, and there's a magnet that's kind of glued in place here. Well, so what we've got going on in the circuit is, given the direction that the battery is set up, the direction of conventional current, which would be, the flow of the way positive charges would go. Of course, we know electrons go the other way, but positive charge would go this way. If it were the thing that moved. So conventional current in the circuit goes this way. So I've drawn that in there. And that current is running in the presence of a magnetic field because we have a magnet nearby. So since the north side points up, you'd have magnetic field lines pointing in this direction up out of this magnet. They come back into the magnet on the south pole, but that's not going to be so relevant for us up here. So what ends up happening is you have this current here passing through a region of space where there's a magnetic field that's pointing up toward the top of the board. And so to figure out what it happens, or what's going to happen with this, I'm going to introduce what's called a right-hand rule. And so the idea is, it goes like this. You use your right hand, think about it like this. Current, put your thumb in the direction of the current, index in the direction of the field, and middle in the direction of the force. Current, field, force. Current, field, force. Really, this is a cross product. A cross B is C. Okay, so we're just using this as a little quick crutch for doing the cross product. And so what we have here on the bottom segment of wire, we have current going this way through a field that points this way. And so what that means is there's going to be a force into the board. So I'm going to put here on this segment of wire, there's going to be F magnetic into the board. I'm just going to say that it goes in, right? Now, if you look up on the top segment of the wire, the current is flowing this way through a field that points up still. That force is going to come out, current, field, force. That's going to be out. So up on this segment of the wire, F mag is going to be out. And so what's going to happen then is this whole loop, this circuit loop, is going to get pushed into the board at the bottom and out of the board at the top. So it's going to want to rotate. So you have kind of the beginnings of a motor. You'll have to do some tricks to keep it running, but you have the beginnings of a motor because you're going to push in here and you're going to pull out there. So it's going to rotate. Okay. It turns out these segments here, if the field's pretty much pointing straight up, they won't feel any force because then you have current running along the field. Right? So anytime you have charge moving along the field lines, you won't have any magnetic force. You need that charge to be flowing perpendicular to the field. So again, you have the beginnings of a motor here. Another context in which this comes up is when you have two circuits that are just operating nearby each other. So let's say we got like circuit A and circuit B. Well, so circuit A, for example, is running a current this way. So there's a current that's operating. Now we learned earlier that when you run current through a loop of wire like this, that generates magnetic field in the space around it. And so within the interior of this loop, you would have current or magnetic field going into the page. Right? Magnetic field would be going into the page. And then coming on the outside of this loop, loop A would be generating magnetic field that comes out of the page here. Right? So all around here you'd have a magnetic field coming out. Well, why that's important is, so in the space around on the outside of loop A, there's magnetic field coming out of the board, out of the page. Well, so that's going to be especially relevant in this nearby segment of circuit B. So what happens is circuit B is also running current, and that current's going this way. Right? But what that means is locally here we're running current this way through a region of space where the field is coming out of the page. So if we use this right-hand rule, we'd have current this way, field coming out. So the force on this segment of wire would actually be away. And so what happens is these nearby circuits will push each other away, would repel, right? So this would be your F magnetic, right? So this thing would get pushed away. You can actually reverse the argument. So like what I did here was I treated circuit A as though it was a source of fields, and then circuit B had to deal with the fields and it gets shoved away, right? Well, you can actually reverse the argument. So let me erase these markings here. And let's reverse the argument and let's use B as the source of field, and we'll see how A responds to it. So circuit B has a current going like this. So circuit B is itself going to generate fields that go into the page here and out of the page elsewhere. Well, what that means then for this segment of wire that's nearby, because it would be the one most affected, you have current going this way through a region of space where field's coming out, and so you're going to get so current this way, field out, force then would be up away. So you can see that this top circuit would get repelled by the bottom circuit. So F mag. Well, we already saw in the first run through that circuit A pushed circuit B away. Well, for every action there's an equal and opposite reaction, so circuit B would have to push circuit A away, and we've just kind of proven that another way by running through the argument again about circuit B making fields that circuit A has to deal with. So that's how magnetic forces work. You need to have charge moving in a direction perpendicular to a magnetic field, and then that moving charge will feel a force in this particular direction. Current, field, force.